Welcome back friends in my YouTube channel TechTide Digital Lifestyle for our Induction Motor Complete course, and today in Day 7 we will study speed control methods and performance characteristics of an induction motor. Please like and subscribe my YouTube channel before start watching. This topic is very important for industrial applications because many processes such as conveyors, pumps, fans, and compressors require variable speed operation, and it is also frequently asked in ETO and COC examinations. We will begin by revising the basic speed equations and then move on to different stator-side and rotor-side speed control techniques, including modern variable frequency drives. First, let us understand why speed control is required. In many industrial processes, the load does not always need to run at full speed. Sometimes lower speed is sufficient, which saves electrical energy and reduces wear and tear on mechanical parts. Speed control also allows smooth starting and stopping, better process accuracy, and improved overall efficiency of the system. Therefore, modern installations almost always use some form of speed control rather than running motors directly at constant speed. Before discussing control methods, recall the speed equations of an induction motor. The synchronous speed depends only on supply frequency and number of poles and is given by N equals 120 times frequency divided by poles. The actual rotor speed is slightly less and is equal to synchronous speed multiplied by 1 minus slip. Slip is the fractional difference between synchronous speed and rotor speed. These equations show clearly that if we want to change motor speed, we must change either the supply frequency or the number of poles, or affect slip by electrical methods. Speed control methods can be broadly classified into stator-side and rotor-side control. On the stator side, the most effective method is to change the supply frequency, because synchronous speed is directly proportional to frequency. However, when frequency is changed, voltage must also be changed in the same proportion to keep the air gap flux constant, and this is known as constant V over F control. Pole changing is another stator-side method, where the stator winding is reconnected to change the number of poles, resulting in discrete speed steps rather than smooth control. Voltage control alone can also vary speed slightly, but it is inefficient for wide range control. Rotor-side control methods are mainly applicable to slip ring induction motors. By adding external resistance in the rotor circuit, slip can be increased and speed reduced, but this method wastes power in resistors and is not efficient for continuous operation. Slip power recovery systems capture the slip power and feed it back to the supply, improving efficiency. Cascade connection is another classical method where two motors are mechanically or electrically coupled to obtain different speeds. In modern industry, the most widely used method is the variable frequency drive, also called VFD or inverter drive. A VFD converts fixed frequency AC supply into DC using a rectifier and then converts it back into AC at variable frequency using an inverter. By controlling both voltage and frequency in the proper ratio, the motor can operate over a wide speed range with high efficiency and good torque capability. VFDs also provide soft starting, braking, protection, and energy saving, which is why they have almost replaced older mechanical or resistive speed control methods in many applications. Now let us look at performance characteristics of an induction motor, which describe how different quantities change with load. The most important curves are speed versus load, torque versus slip, stator current versus load, and efficiency versus load. The speed load curve shows that speed decreases slightly as load increases because slip increases. The torque-slip curve we studied earlier shows how torque varies from no load to starting condition. The current load curve shows that stator current increases with load, and the efficiency load curve shows that efficiency is maximum near rated load. When load on the motor increases, the rotor slows down slightly, which increases slip. Higher slip causes more rotor current to flow, which increases electromagnetic torque to balance the load. At the same time, stator current also increases to supply the extra power required. When load decreases, the opposite happens. Slip reduces, current reduces, and speed moves closer to synchronous speed. This self-regulating behavior is one of the most useful features of induction motors. From ETO and COC exam point of view, make sure you can list and explain all speed control methods, compare stator-side and rotor-side control, explain the working and advantages of VFD, write speed equations, and draw basic performance characteristic curves. These are common theory and short answer questions. To summarize today's Day 7 lecture, we have studied why speed control is required, basic speed equations, stator-side and rotor-side control methods, modern VFD-based control, important performance curves, and how load affects speed and current. In the next lecture, day -8, we will cover testing of induction motor and performance calculation, which includes no load and blocked rotor tests, so stay connected with the playlist and keep learning. Thank you for watching this video. Like and subscribe my YouTube channel TechTide Digital Lifestyle, hit bell icon and comment on video.